Homeostasis is the remarkable ability of living systems to maintain internal stability, even as external conditions change. It's a fundamental process that allows organisms to function optimally, from the single-celled to the most complex. Homeostasis regulates critical variables within preset limits, contributing to the overall health and balance of the organism. Homeostasis is a fundamental biological concept that describes how living systems maintain stability and balance in the face of external changes. The term, homeostasis, comes from the Greek words, homoios, meaning similar, and stasis, meaning standing still. It was established in the 1930s by pioneering physiologists. The core principle of homeostasis is that living organisms have self-regulating processes that work to maintain optimal internal conditions, even as the external environment changes around them. Homeostasis is a key driver of organic action. Living systems actively resist changes when they are already in an optimal state of equilibrium. Understanding the mechanisms of homeostasis is crucial for studying how biological systems function and adapt over time. Homeostasis is crucial for protecting organisms from external variations and maintaining the right chemical environment for cellular function. It acts as a shield, creating a buffer between the organism and its environment, allowing it to thrive even as conditions change. By constantly adjusting and preserving life, homeostasis ensures the survival of organisms, enabling them to adapt and continue living in dynamic conditions. Homeostasis is essential for the proper operation and thriving of life at the cellular level. The core components of homeostatic mechanisms are receptor, control center, effector, and feedback loops. The receptor is the sensing component that detects changes in the environment. The control center processes the information from the receptor and determines the appropriate response. The effector is the target that implements the necessary adjustments to maintain homeostasis. Feedback loops are the communication channels between all the components, allowing for continuous monitoring and adjustment. Understanding these core components is crucial for understanding how the body maintains balance and stability in the face of internal and external changes. The slide provides an overview of the three main types of feedback systems: negative, positive, and feed-forward. Negative feedback is the most common type, and it opposes change to restore balance. This is seen in many biological systems. Positive feedback amplifies change, and is less common but crucial for certain processes. Feed-forward systems anticipate changes before they occur, and act preventatively. The slide includes visual icons and brief descriptions for each type of feedback system. I will use these key points to guide my explanation of the different feedback mechanisms and their applications. Normal body temperature is around 37 degrees Celsius or 98.6 degrees Fahrenheit. The hypothalamus serves as the control center for thermoregulation. Receptors like baroreceptors and thermoreceptors detect changes in temperature and pressure. Effectors like sweat glands, blood vessels, and muscles help the body respond to maintain a normal temperature. Thermoregulation is the body's complex system for maintaining a stable internal temperature. The key mechanisms are heat generation, heat conservation, and heat loss. Heat generation includes muscle contractions like shivering, increased metabolism, and hormonal adjustments. Heat conservation involves blood vessel constriction, behavioral responses, and changes in body positioning. Heat loss occurs through sweating, blood vessel dilation, and respiratory cooling. Humans have also developed cultural adaptations like clothing, shelter, and external heat sources to further regulate body temperature. This slide provides an overview of these core thermoregulation mechanisms that allow the body to maintain a healthy, stable temperature. The human body must maintain a careful balance of fluids and electrolytes to function properly. This balance is controlled through several key mechanisms: water regulation to maintain proper hydration levels, precise control of ion concentrations like sodium, potassium, and calcium, the kidneys filtering blood and adjusting water and electrolyte levels, hormonal signals that regulate fluid retention and excretion. Understanding these fluid and electrolyte regulation systems is crucial for maintaining overall health and preventing imbalances that can lead to serious medical issues. I'll go into more detail on each of these key mechanisms in the upcoming slides. The human body has several mechanisms to regulate pH and maintain a normal blood pH between 7.35–7.45. Buffer systems provide immediate chemical regulation of pH. Respiratory control adjusts CO2 levels through breathing rate to influence pH. Renal compensation provides long-term regulation through the excretion of acids and bases. Deviations from the normal pH range can lead to acidosis, too low, or alkalosis, too high. It's critical to understand these pH regulation systems to maintain homeostasis in the body. Blood glucose regulation is a critical physiological process that involves the pancreas and the hormones it produces. Insulin is a key hormone that lowers blood glucose by promoting its uptake into cells. It's produced by pancreatic beta cells when glucose levels rise. Glucagon is another important hormone that raises blood glucose by triggering the liver to release stored glucose. Glucagon is released when blood sugar drops too low. The pancreas serves as both a sensor and an effector, containing specialized cells that monitor and respond to changes in glucose levels. Understanding how insulin and glucagon work together to maintain blood glucose homeostasis is crucial for managing conditions like diabetes. The human body maintains a range of normal values for key biological variables like temperature, blood pressure, blood glucose, and oxygen levels. These normal ranges have upper and lower limits. Crossing those limits triggers corrective actions to restore homeostasis. The optimal conditions within these normal ranges are called homeostatic plateaus. These normal ranges can vary based on factors like age, health status, and environment. Understanding these homeostatic ranges and plateaus is important for monitoring and maintaining good health. Homeostasis is the body's ability to maintain a stable, balanced internal environment. When homeostasis fails, it can lead to acute, life-threatening situations or chronic, progressive health issues. Acute failure requires rapid intervention to prevent fatal outcomes. This could be something like a severe allergic reaction or organ failure. Chronic disruption gradually impairs multiple body systems over time, leading to deteriorating health. Examples include chronic diseases like diabetes or heart disease. Many diseases reflect underlying homeostatic imbalances. Understanding the regulatory mechanisms that maintain balance is key to treating and preventing illness. The images on this slide depict critical medical emergencies and chronic disease states that can occur when homeostasis fails. The slide highlights some of the cutting-edge research and applications in modern medicine and biomedical engineering. The first point discusses the artificial pancreas, a system that continuously monitors glucose levels and automatically delivers insulin as needed, helping to manage diabetes. Next, we have temperature-responsive systems, drug delivery devices that can release medications based on specific changes in body temperature. The third point covers biomedical sensors, devices that mimic biological receptors to monitor various health indicators. Finally, the slide looks ahead to space medicine goals in 2050, where the aim is to develop homeostasis solutions to support long-duration space exploration missions. These advancements demonstrate the rapid progress being made in fields like biosensing, drug delivery, and autonomous medical systems to improve human health and enable new frontiers of exploration. The central theme of this presentation is the delicate balance that underpins life and living systems. We'll explore 4 key principles that illustrate this balance: internal stability, integrated systems, evolutionary refinement, and balance maintenance. Internal stability refers to the ability of biological systems to maintain a steady state, which is crucial for survival. Integrated systems highlights how different functions in the body work together in a holistic way to regulate the organism as a whole. Evolutionary refinement shows how living systems have been optimized over millions of years to achieve remarkable efficiency. Balance maintenance is about the need to strike a balance between extremes, as going too far in one direction can lead to dysfunction. Understanding these principles of homeostasis provides valuable insights into health, medicine, and the remarkable engineering of nature.